Good afternoon, everyone. I am Ella, and it's my pleasure to welcome you on behalf of eMobility Plus and First View Group to our webinar on designing electric motors and drivetrains with multiphysics simulation. First and foremost, I would like to express our gratitude to our partner COMSOL for their invaluable support in making this webinar possible. Before we begin, allow me to introduce our session expert, Mr. Sharath PN, Technology Specialist at COMSOL Multiphysics Private Limited. Mr. Sharath holds a master's degree in machine design from BMS College of Engineering, Bangalore. He previously worked at Tata Consultancy Services, where he focused on mechanical integrity assessments of Siemens gas turbines. Now, at COMSOL, he specializes in using multiphysics simulation to solve complex design challenges. Now, let me give you a quick overview of today's session. With the rise of electric vehicles, designing efficient motors has become crucial in improving vehicle range, reducing battery requirements, and optimizing power density and costs. Multiphysics modeling and simulation are essential in achieving these goals. COMSOL Multiphysics, along with its AC-DC module and battery design module, provides powerful tools to simulate various aspects of electric motors and drivetrain components. The software is designed to capture the complex interplay of physics in motors, including electromagnetics, thermal effects, fluid dynamics, and structural mechanics, while offering optimization capabilities to speed up product development. During this webinar, Mr. Sharath will walk us through how COMSOL multiphysics can be applied in the R&D of electric motors and drivetrains. Following the presentation, we will have a Q&A session where you can submit your questions in the Q&A box. Mr. Sharath will address them at the end of the session. So before we dive into the presentation, we would like to show a brief video highlighting how COMSOL supports the automotive industry. May I request my team to kindly play the video now?
Developing designs and performing experiments virtually is both cost and time efficient. With COMSOL Multiphysics simulation software, you can be sure your results accurately represent the real world. By studying multiple physical effects on one model, no matter the order in which you combine different physics, the software handles them together and solves the mathematical and numerical model equations and provides you with the model results. The entire simulation process takes place in the same software environment. You only need to learn one workflow, no matter the physics involved or the nature of your experiments. Depending on the scenario, you may want to model single physics, one-way multiphysics, or fully coupled multiphysics. The COMSOL software offers all three, and the true advantage of COMSOL Multiphysics is the ability to model unlimited multiphysics, where all physics in a model interact, affect each other, and together influence the model results. If you need to add any physics, including your own equations, to your model, you can. The application builder in COMSOL Multiphysics gives you the tools to build your own simulation apps. The Startup Wizard and drag and drop functionality help you quickly turn your models into simulation apps with customized user interfaces, restricted inputs and outputs, report generators, and more. This way, you can spread the advantages of simulation to colleagues and customers by compiling your apps as standalone executables via COMSOL compiler, or by making them accessible by web browser via COMSOL server. Understand, predict, innovate, and optimize your processes and designs with COMSOL Multiphysics.
Thank you, team, for playing that video. So now that you've all been introduced to COMSOL's capabilities, I would now like to welcome our expert, Mr. Sharath, to take you through the details and through his presentation. Over to you, Mr. Sharath.
Yeah, thank you, Ms. Ala, for that lovely introduction and for that very informative video. I hope my screen is visible to all the attendees.
Yes.
Okay, yeah, great. So yeah, so the main focus of today's session would be to look at how we can model, simulate, and optimize different components of our electric drivetrain. So basically, COMSOL is a general purpose simulation tool. right? So where you can model different aspects of your electric drivetrain, right? So be it the electric motors of different configurations. So it can be the power electronics components, so that are housed between the batteries and the motors, and also the batteries themselves, right? So these battery modeling can range from simple electrode modeling until the battery pack level modeling as well. So you can look at different aspects of battery modeling, such as the thermal management or even the thermal runaway kind of events, right? And how we can avoid such events. So in that case, so we all of us know that the electrification of our drivetrains is picking up at a very rapid pace, right? And to in order to have a very efficient motors, it can be inverters, the power electronic components, or even the batteries. So that becomes very crucial to have an efficient overall system, right? So that would in a way reduce the greenhouse gas emissions, and that will lead to overall profitability of the organization and at an individual level as well, right? So in today's session, so we'll focus more on the electric drivetrain components and how those components can be modeled and optimized for better efficiency, so within the COMSOL multiphysics tool as well, right? So keeping in mind the aspect of bandwidth, I'll just be disabling my video feed as of now. All right. So, like I was mentioning before, so COMSOL Multiphysics provides one software environment to model any kinds of physics, right? So it can be single physics and also the multiphysics part as well. So let us just discuss briefly why multiphysics, right? So let us take the example of an electric motor itself. So when you are starting off with the design of an electric motor, you start off with the basic electromagnetic analysis. But very quickly you come to know that because of various losses, so these losses lead to temperature rise, right? So you'll have to contain this temperature rise in some form or the other. So that is where the thermal management aspect comes in. So in COMSOL, you can couple the electromagnetic aspect with the flow aspects to design any sort of cooling systems. Right? So this can be active cooling or passive cooling. So once you have designed the cooling systems, so you now know that there can be sources of structural forces within the motor because of various electromagnetic forces. And these varying forces can lead to vibrations and noises. Right? So in order to reduce such vibrations and also to reduce the noise level coming out of your motor, you can perform a coupled electromagnetic, structural mechanics, and acoustics analysis, right? So in a sense, within COMSOL, you can perform end-to-end analysis for the electric motors or even the power electronic components or the battery systems as well, right? So in that sense, COMSOL Multiphysics provides one single software environment for any kind of engineering applications. Yeah, so before we start off with the actual session, in order to gauge the kind of audience that we have today, I would request the team to launch this first poll question. So this is just to understand if the audience we have today is a regular user of simulation tools, or if you're evaluating simulation tools for your any upcoming project or ongoing project, or if you're just attending the session out of your personal interest, or if you're completely new to multiphysics simulation kind of applications.
So I'll keep the poll open, but I'll hide it from the screen, and so that you can continue with your presentation, so that the audience can keep taking the poll throughout the webinar in our poll section.
All right, yeah, that's good. Yeah, so let us now discuss how COMSOL physics can help you when it comes to the electromagnetics simulation of your electric motor. Right? So COMSOL offers dedicated features to model multiple kinds of conductors, right? So it can be solid conductors or multi-ton coils or single-ton coils. So COMSOL offers multiple patterns in which you can model your magnets. Right? So there are features to model your multi-phase stator windings, or you can also have your own user-defined stator windings as well. So there are multiple methodologies in which you can compute the losses. So these losses can be either due to hysteresis losses or resistive losses, right? So there are empirical formulations to compute such losses, such as the Steinmetz or the Bertoldi formulation. Or if you have any other formulations, user-defined formulations, you can define that within COMSOL as well, right? So we can, in order to reduce the complexity of your particular simulation model, you can also go with the sector modeling approach as well, right? And so not just any standard configuration such as the radial flux motors, but you can also model any axial flux motors or the linear motors, right? And coming to the more structural aspects, so you can compute the torque calculation, right? So we have features such as the arcuate torque calculation functionality to obtain the electromagnetic torque that has been generated at the stator and the rotor interface. So having accurate magnetic material models is very important to obtain a proper results. Right? So for that, COMSOL offers a large material library when it comes to hard and soft magnetic materials. So there are material models to compute magnetic saturation, the magnetic losses. So this can be different kinds of hysteresis losses. And it is very important to consider the temperature dependence on your material properties. Right? So your material dependence can properties can vary very widely at different temperatures, different ambient temperatures or the model temperatures. So you can consider these aspects as well within your simulation model. As I was mentioning before, so we are aware, very much aware of the radial flux motors, right? So that are the conventional configurations that we have. But not just these configurations, but you can also model the more modern and more efficient configurations such as the axial flux configurations, right? So this is becoming more popular because of its characteristics of high power density, and you can use these kinds of configurations where you need such properties, right? So it can be electric trucks and so on. So all these configurations can be modeled. So in effect, so if you have the particular geometry, so you can model those if it is physically feasible. So that is the kind of flexibility that COMSOL offers as a simulation tool. So we discussed about the electric motors, right? So if you look at the second aspect of your drivetrain, so which is the power electronics components, so you can model those aspects within COMSOL as well. Right? So because of increased demand when it comes to your electric vehicle applications, so this needs more compact handling of your power electronics devices and needs better thermal management as well. Right? So for that, you can carry out such simulations within COMSOL Multiphysics. So we'll see some of those aspects as well. Yeah. So the third, but not the third and most important aspect of your electric drivetrain is the battery aspect. Right? So within COMSOL, you can model your batteries at very electrode level, where you can do any sort of heterogeneous kind of simulations, right? And you can homogenize these properties and also perform your analysis at the battery pack level as well, right? So such as the thermal management of your battery pack and also thermal runaway kind of analysis, right? So yeah, so once again, COMSOL supports different forms of study types as well, right? So be it ranging from a very simple stationary study until the time dependent study and frequency domain studies and so on. Okay, now that you're aware of the different capabilities when it comes to the electric drivetrain simulations, so just to kind of understand what kind of simulations that you are into, so I would request the attendees to answer this poll question as well. So what aspects of motor would you like to model? Right? So is it the electromagnetic losses, the thermal effects and the efficiency, or if it is the noise and the vibration aspects, or if it is the optimization part? So COMSOL offers very powerful optimization algorithms as well, right, to improve the efficiency uh, of your particular configuration. Or if there are any other aspects of the electric motor or the electric drivetrain that you're looking to model, you can enter those as well. All right. So moving on. So if we come back to the electromagnetic modeling of the electric motors itself, right? So COMSOL offers features and functionalities to compute the losses. So these can be hysteresis losses or eddy current losses. So within the hysteresis losses, it can be either eddy current losses or iron losses, or what we refer to as the copper losses due to the resistive loss components as well. Right. So for that, COMSOL offers the Steinmetz and the Bertotti loss formulations. So and then we have to compute those losses. So we have the time to frequency losses functionality as well, right? So which is based on the FFT functionality. So you can see here. So COMSOL. So if I can say, it's not like a black box, right? So you basically know what are the equations that you're trying to solve to compute your, for example, in this case, the losses. right? So here you can see the Steinmetz empirical formulation that is there here. And you can also see the different variables and inputs that you need to give into the software in order to calculate those equations. Right? So COMSOL in that sense is an open box. So you can also modify these equations as well. So in case such a need arises. So once we have computed the losses because of the different reasons that we discussed just now, so that would lead to temperature rise, right? And so once again, the material properties, so especially, for example, the copper conductivity and the magnetization, they are all heavily dependent on the temperature of the either the coils or the magnet. Right? So you can also consider the temperature dependent characteristics within your motor modeling as well. Right? So here you can see one such example here. In this case, the coil wire conductivity has been expressed as a function of temperature as well. Right? So that would lead to more accurate results for your particular simulation model. Right? So this is for the coil wire conductivity of your multi-phase winding feature that is present. And we'll look into more of these features and functionalities during the demonstration session as well. Right? So where I'll open the COMSOL software and demonstrate how we can set up a basic model of an electric motor. Yeah, so once the electromagnetic simulation is done, so the end step would be to obtain the most important functionality of the motor, which is the torque calculation. Right? So for that, within the rotating machinery magnetic interface, the physics interface, we have this arco torque calculation feature. So which has several predefined variables, right? So to compute the radial force density, azimuthal force density, and also the magnetic flux as well. So if you go to comsol.com, or if you opt to choose the trial license, you can also refer to the different tutorial models that we have. So be it the 2D models or the 3D models. You can refer to these models and see if it is very relevant to the kind of simulations that you are trying to do within your teams. Yeah, so until now, we saw the various electromagnetics aspects of the simulations of the electric motors. Right? So we can also extend the electromagnetic analysis to structural mechanics aspects as well. So any sort of three-phase current, so that would produce a lot of torque fluctuations at the bearing side, right? So these torque fluctuations are transmitted to the shaft and also to the motor housing as well. And to accurately determine the remaining life of the different components of your electric motor, it is very important to do a vibration analysis as well to find out the fatigue life that is remaining. So you can extend your electromagnetic analysis to include such fatigue life calculations, or also a vibration analysis as well. Right here, you can see the stress distribution in the housing and also the rotor velocity as well for different rotational speeds. So you can also model the rotor orbits for the bearings. Right? And so within COMSOL, we also have the rotor dynamics module, so which provides a functionality to model different kinds of hydrodynamic bearing or the roller bearings as well. Right? So this considers the functionalities of both the structural as well as the thin film flow aspects as well. Yeah, so this is one such example for that. Yeah. So now that we have seen the different electromagnetics and the structural mechanics aspects that you can model for your electric motor, so let us now see one case study from one of our long-term users. So this is from Volkswagen Castle. Right? So here they're trying to basically optimize for the forces that are acting on the laminates, right? So yeah, so basically by using the electromagnetic and the structural mechanics module, so they were able to evaluate the strength of the rotor laminations, right? So these rotors have very thin laminations, and because of the various electromagnetic forces, so if they are not designed properly, so that can be a hotspot for failure, right? So this is an example of one such coupled electromagnetic and structural mechanics analysis. So in the initial video that was played out, so we also demonstrated on the application builder functionality within COMSOL, right? So here is one such example where the engineers have built a very simple to use simulation application as well, right, based out of their complicated simulation model. And such simulation apps that we refer to can be shared with your colleagues from the different teams as well, right? So that they can perform any kind of validation and testing that needs to be done on the shop floor. So this is one such very good use case for application builder functionality of COMSOL. So in the last update, within COMSOL, within the electromagnetics module, so we have released time periodic electromagnetics functionality, right? So which we refer to as a game-changing approach. So earlier, the time-stepping way of solving motor models, right? So that is the traditional approach of transient analysis, and the rotation of the rotor is modeled by time-stepping, and the effect of the such rotation is observed. Right? But in this time periodic approach, apart from the two space dimensions that we consider, for example, if you are modeling it in a 2D, a third time dimension is also modeled. So in this case, the time is basically split into a series of frames in case of motors and generators. And so that is where we consider the periodicity in operation. Right. So what I mean is the rotor comes back to the same state after each rotation. So what this opens up to is so in by basically consider this kind of time periodic approach. So you can do multiple parametric studies, right? So we can extract efficiency maps and temperature maps. We can also include multiphysics aspects of it very simply, right? So we can include basically extend the electromagnetics analysis with heat transfer, and you can also perform structural mechanics analysis to obtain the deformations at various locations and for vibrations as well. Right. So not just the multiphysics, you can also optimize for different objective functions as well, right? Such as the topology optimization or the parameter or the shape optimization. Right. So we use this approach for models or any phenomena that require many cycles to reach a steady state or a stationary state. Right. So this is one such game-changing approach that gives you very accurate results in a very short span of time. Yeah, so in continuation of the previous slide, so where we were referring to the multiphysics aspect of it, right? So here you can see one example of it. We are basically have solved the electromagnetic loss distribution in the entire stator and the rotor domains of the motor, right? And because of these losses, we are also able to compute the temperature field at various operating points as well, right? So here you can see the temperature distributions for different speeds and also different peak currents as well. Right? So using this data, we can ultimately plot what we refer to as the efficiency maps for that particular configuration of the motor as well. So this is basically to determine the optimum range of working range for that particular motor. Right? So this can be very easily done by using the time periodic analysis. So we'll see how we can basically set up a simple model of a motor during the demonstration. Right. Extending the multiphysics aspect of it from the previous slide, where we saw the thermal management kind of analysis. So here you can also extend such a study to obtain or to do any kind of noise, vibration, and harshness kind of analysis as well. Right. So here you are able to see the sound pressure level in the surrounding domain of this particular model. So at different operating ranges and also for different harmonics as well. Right. So similarly, you can plot what we refer to as the Campbell diagrams as well. So where we plot the natural frequencies for a different range of working rotational speeds. Right? So this is what we have done, and using this, we really obtain the different critical frequencies where the motor is more prone to resonances. Right? Yeah. So as you can see, we have covered ranging from very basic electromagnetic analysis until the analysis as well. Right? So that is the kind of uh, functionality and the flexibility that COMSOL as a multiphysics simulation software provides to the users. So within the time periodic analysis, we can also include multiple optimization strategies as well. So here in this animation, you can basically see one such implementation for topology optimization. Right. So here the objective was to basically reduce the torque fluctuations by up to 2.5 times. So that was the objective function. Right. And so at the same time, we were also able to reduce the amount of iron material used. Right. So here you can see at the end of the optimization, we were able to reduce some iron material. And at the same time, by optimizing, we were also able to reduce the maximum stress right, by 14%. So this is the kind of optimization functionality that COMSOL provides. So this is in particular for the topology optimization example as well. Right? So if you look at other functionalities when it comes to optimization, so COMSOL supports parameter optimization and also the shape optimization as well. Right? And so the support for the objective function can come from any of the underlying physics. Right? So it can be the objective function can be to increase the torque output when it comes to the electromagnetics. So it can be to reduce the overall temperature distribution when it comes to heat transfer. So the objective function can also be to reduce the stresses that have been induced because of various electromagnetic forces when we look at the structural mechanics point of view. Right? So the in a sense, the objective function can come from any of the underlying optimization. Right? So here you can performed on an axial flux motor. Right? So this is an example for topology optimization. And if you look at an example for parameter optimization itself, so where the objective is to maximize the torque output, right? And we basically perform parameter optimization in cases where we are very easily able to parameterize any aspect of the motor, right? So it can be geometric aspects, it can be performance aspects, it can be material property aspect as well. So in this case, the control variables are the tooth width, so that you can see here. The tooth width, the back iron thickness, so it can be the magnet width, it can be the magnet height. So anything that you can parameterize, so those can be your control variable. Right? And the constraint here was the coil area conservation. So whatever the coil cross-section area that you see, so that we had to maintain constant, right? So that was the constraint. And so at the same time, we wanted to reduce the magnet area by 10%. Because as you might know, the magnet material is the most expensive component of your electric motor, right? So if you can optimize it by reducing the amount of magnet used in your electric motor configuration, so that can lead to large cost savings, which can be passed on to the end user as well. Right? So these were the constraints. And if you look at the results for such a optimization, so here you can see basically the torque output from this particular motor. Right? So the initial design is seen in the blue curves, and the parameter optimized can be seen in the green curve. Right here you can see, since the objective was to increase the torque output, that particular objective has been achieved in a sense. Right? So you can see higher values for the parameter optimized case. And you can also see the shape optimized results as well. So we typically go for shape optimization when it becomes very difficult to parameterize any of the geometric aspects of your model. Right? So for example, it is very, if you look at this picture itself, it is very hard to parameterize the different geometric features of this particular magnet domain. Right? So that is where we go with the shape optimization, where we try to change the shape of this particular outer boundary of the domain of interest. Right? So yeah, here in this particular example of shape optimization, the objective was to minimize the torque ripple. Right? And here you can see the torque output for this particular shape optimizations. You can see the torque ripple that has been reduced. Right? So if you look at the maximum torque minus the minimum torque, the whole torque range has been reduced. Right? And that has been done by basically changing the outer boundary of the magnet. Right? So I can also once again demonstrate on the animation as well, if you can see. So this is the animation of the shape optimization that has been performed by keeping this particular objective of reducing the torque ripple. So this is an example of the magnet shape optimization. Right. So now we'll quickly switch over to the live demonstration of setting up a very basic example of a 2D motor. Right. So we'll be basically making use of the time periodic interface, and we'll couple the electromagnetics with heat transfer to see what is going to be the effect of losses on the temperature rise. Right? So we'll also see how we can look at the efficiency maps. So this efficiency is in effect plotted as a function of speed and torque. Right? And so by including the thermal effects and without including any of the temperature effects, what is going to be the difference? So we'll look into those aspects as well. So let me just quickly open the COMSOL software. All right. So I have already opened the software, right, with the geometry already imported, right? So COMSOL. So this is a general layout of the COMSOL software. Right? So we have the model builder that has the different steps that you need to basically take to set up your simulation model. Right? So this can be importing geometry or creating geometry within COMSOL. So this can be assignment of different materials to the different domains. So it can be, applying boundary conditions uh, by use of different physics interfaces. So this can be creating mesh, or you can import mesh from any of the external sources as well. And finally, the study types and the results and visualization aspects of it. So for each of these nodes, you can see the corresponding settings as well. Right? And finally, we have the graphics page, so where we visualize our particular geometry. And yeah, so we also have the ribbon tab on the top where we can access the different settings for each of these aspects, right? So it can be for different geometry aspects, so the materials, physics, mesh, and finally the study and the results as well. Yeah, so when it comes to the electromagnetics, so COMSOL offers ready-made geometry parts as well for different configurations of electric motors. So it can be in the 2D or the 3D domains as well, right? So COMSOL so using the COMSOL part library, I've already imported one configuration of internal rotor with the surface mounted magnet. So this is the configuration. And I already also have the external stator as well, right? So this is the slotted stator that we have with the coils and the laminations as well. Yeah. So now within this, we'll see how we can, apply the different boundary conditions to set up our motor model, right? Yeah, so the first step would be to add a physics interface, right? So for that, you can directly go to the physics tab on the top ribbon, and here I'll click on add physics. So here the physics interfaces, you can see they are based on the different modules that are supported within COMSOL Multiphysics. And for our application, I'll go to the AC/DC module, and within that, I'll go to electromagnetics and mechanics. Yeah, so we have the different physics interfaces that basically support modeling different kinds of electrical machines. Right? So this can range from electric motors to transformers or different kinds of switches and so on. Right? So for our application, so I'll add the magnetic machinery rotating time periodic physics interface. So I'll click on add to component one to add this particular physics interface to our component. Yeah. So similarly, you can include different multi-physics aspect of it as well, right? So you can also see the magnetostriction physics interface that we have. Here you can couple the electromagnetics if you want to see any with the structural mechanics physics interfaces to model any deformations due to the magnetic fields. Similarly, magnetomechanics. So we have the electromagnetics and fluids and so on. Yeah. So for this session, we'll restrict ourselves to electromagnetics and thermal aspects of it. Right? So now we have the magnetic machinery time periodic interface that has been added. Right? So once I click on it, so here I can see the relevant settings as well. So within COMSOL, we can parameterize the different performance parameters of our machine. Right? So in that sense, so I already have a list of parameters that are relevant to my electric motor. Right? So this can be the number of poles uh, relevant to the magnet. So the number of slots, the coil slots. So then we have the out of plane thickness of this particular motor, the initial electrical angle, right? So the peak current, electrical frequency, the shaft speed, and so on. So all of these parameters are basically parameterized. All these values are parameterized, and I'll be using these parameters for different boundary conditions and the different motor settings. Yeah. So in that sense, I'll go to the magnetic machinery physics interface, and now so it is asking for out of plane thickness. Right? So I'll just enter the particular parameter that I already have created. So which is L. Right? So the next thing is the time periodic electrical frequency. Right? So the time periodic settings. So for that, I once again have electrical frequency that has been parameterized, which is f underscore el. So it is asking for the number of time frames that I want to split my periodic time. Right? So I'll enter n frames. So this is once again parameterized. Yeah. So then coming to the the number of poles, so which is relevant to the magnet part. So I'll enter NP, which is again a parameter. Right. So once I have this, so I'll click on add rotational boundary features. Right. So once I click on it, so COMSOL adds a couple of default boundary conditions. Right. So which is the rotational continuity pair. Right. So here you can see highlighted in the purple color, which is on the edge. Right. So it is basically establishing continuity between the rotor and the stator of this particular motor, and we also have the rotational periodicity as well. Right. So to basically reduce the numerical load on the computer, I have considered only the 180-degree sector of this particular electrical motor, and this boundary condition is basically establishing continuity on this sector boundary. So that is what we have. So let us see what other boundary conditions are needed to set up a basic electric motor. So if I right click on the magnetic machinery interface, so I have multiple options, right? So these are the different boundary conditions and also the domain conditions that are needed to set up the model. So the first thing that I would add is the rotating domain. So here is where we specify what domains will be rotating. Right. So yeah, COMSOL is intelligent enough to detect these rotating domains. Right. So since we have imported these features, the geometry from the internal part library itself, so it has detected those domains. Yeah, so here you can specify the time periodic rotation as well. Right? So if it is going to be a synchronous pole pair or a full mechanical revolution, or if you are modeling any non-rotating kind of electric motor, so it can be a linear configuration that are mostly used in conveyor systems and so on, right? So it can be non-rotating or it can be any other user-defined time periodic rotation as well. So for now, I'll leave it at synchronous pole pair, and the rotation direction is self-explanatory. Yeah. So the next thing would be to model the laminated core. Right? So I'll add that particular boundary condition, and I'll select the laminated cores. Right. So which are basically when it comes to the rotative part, so which is this domain, and also the top domain from in the stator part. Right. So I'll click on it, and here you basically have to select the magnetization model. Right. So once again, within COMSOL, you have you can either go with the pH curve or with the relative permeability option. So if we go to the materials, and so if I go to soft iron, for example, so within this particular soft iron, I can look at the pH curve for this particular material, right? So if I click on the interpolation and plot this particular curve, you can see the pH curve that has been plotted. Right? This is on the magnetization aspect of this particular lamination. So I'll be going with the pH curve route, and the magnetic field normal and the co-energy density will be coming from the material itself. Yeah, so like we were discussing in one of the slides earlier, so there are multiple loss formulations that you can go for. So the Steinmetz and the Bertoldi are the inbuilt empirical loss formulations, and you can go for any user-defined approach as well. So that is on the laminated core aspect. Now the next step would be to model the magnet itself. Right? So I'll add the magnet, and so here it is asking me to select the relevant domains. So which are the magnet domains? So since this is the surface mounted configuration, I'll be selecting all the relevant magnet domains here. Yeah. So now it is asking for the direction method, right? So yeah. So you can specify the north and south boundaries to specify the polarity, or you can specify by domains as well. So if you have separate domains for the north and south pole, right? So I'll go with specify north and south boundaries, and the pattern type will be circular in this case, right? So it can be linear, so depending on the application. Now if I expand the magnet feature, now it is asking me to specify the north and south boundaries. So I'll have to specify that basically. So I'll specify this as a north boundary and this as a south boundary. Right. So since I have already specified the type of periodicity as well, which is repeating, or you can also go for the alternating as well. Right. So since in this case we need alternating north and south boundaries for modeling this particular configuration, so I'll change the type of periodicity to alternating. Right? So once again, if you have to define the constitutive relation for this particular magnet, so we are taking it from the remnant flux density, right, and where the permeability is coming from the material itself, right? So yeah, once again, electrical conductivity is coming from the material, and you can also consider the loss model, right, for that is coming from the resistive heating as well. Right? Yeah. So this is on the magnet modeling aspect of it. So next, let us see how we can specify the electrical excitation. Right? So yeah, if I right click on the magnetic machinery, so next I have the multi-phase winding. Right? So this is what you use to model the electrical excitation. So once again, it is asking me to specify the domains, which are the copper domains. Right? So I'll select all these relevant domains. Yeah, so these are the domains where I'll be modeling the three-phase electrical excitation. Right? So once again, when it comes to the settings of the multi-phase winding, it is asking me for the peak phase current, the initial electrical angle, and so on. Right? So once again, we have the parameter for all of these. So I just enter these parameters. So for the peak phase current, it is IPK. Then for initial electrical angle, I have net underscore underscore ANG. Yeah, so then we have the number of poles, right? So the number of uh, yeah, so it is also asking for the number of poles as well. So winding layout configuration is basically we need to specify it, right? So it is the automatic three phase. So this is the default and most commonly used, right? So I'll just switch it to automatic three phase, and in this it is asking for the number of poles. Right? So once again, I have the parameter for this and the number of slots as well. And it is asking me for the number of coils per slot. Right? So within the geometry, we already have modeled 2 coils per slot. So I'll leave it as it is. And now that we have the different parameters, I'll now click on add phases. Right? So now it has added the 3 phases that are needed for the three-phase excitation. So here you can also see the coils that are going to be excited for each of these phases. Right? So for phase 1, it is those 3 coils. So for phase 2, and similarly for phase 3. So even in the individual phases, you can also determine which is the reversed current direction. Right? So you can specify that as well. Yeah. So I mean, with this we have basically set up a very simple model when it comes to the electromagnetic aspect of it. So similarly, you can also model the different heat transfer aspects of it as well. Right? So if you click on add physics, so we have the heat transfer modules as well. Right? So we have the heat transfer in solids, fluids, and so on, conjugate heat transfer. Right? So all of these can be considered. So keeping the interest of time in mind, so I'll be basically showcasing a solved model that we already have for an already set up model. Yeah, so this already has the physics interface and the boundary conditions for both the electromagnetics and also the heat transfer part. And the multiphysics in this is going to be the electromagnetic heating itself, right? So because of the different losses that we have considered. And the next aspect would be to build a mesh as well, right? So COMSOL offers functionalities to create your own mesh, or you can also create automatic mesh as well. So that is the physics controlled mesh, and that takes into consideration the different underlying physics interfaces, right? So in case you need to account for the boundary layers to basically model the skin depth effect, right? So for that, keeping in mind the different boundary conditions that you have already applied, COMSOL automatically generates the boundary layers that are needed. So similarly for heat transfer or fluid flow as well, right? So then would be to look at the different study steps as well. Right? So here we have basically we have run a parametric sweep for different rotational speeds, right? So different shaft speeds and also for different peak currents as well. So ranging from 3 amperes up until 30 amperes. Now let us look at the results here. So we have the magnetic flux density that we have plotted. Right? So yeah, so we have the magnetic flux density. Then we have the temperature plots that are as a result of various electromagnetic losses that arise. So different forms of hysteresis losses, iron losses, eddy current losses. So this is the temperature distribution that we see close to 390 Kelvin of peak temperatures. Yeah, so then we have the motor efficiency map that we can create, right? So yeah, so since we have basically run a parametric sweep considering different rotational speeds and also for the currents, so we have the results for torque outputs at different rotational speeds, right? So we are plotting those and we have computed the efficiencies, right? So using this, we can basically determine the optimum working range for the electric motor. So similarly, we also have the electromagnetic losses as well, right? So yeah, so keeping the values that have been obtained from this computation, we have also computed the temperature rise, right? So for the same parameters at different speed ranges and also the peak current ranges, right? Yeah, so here you can see the different temperature ranges as a result of different operating parameters. Yeah, so the idea here was to basically showcase setting up of a very basic electrical model in 2D, right? So where we are considering the electromagnetics and coupling it with the heat transfer as well. So similarly, you can extend this kind of analysis with a structural mechanics, a solid mechanics, or or an acoustics interface as well to obtain vibration analysis or different acoustics performance parameters as well. Yeah, so let us now go back to the slides. All right, so until now we saw the one third of the drivetrain component, right? So which is the electric motor component. And so within COMSOL, we saw that we can model different configurations of electric motor and also the different working principles as well, right? So it can be a permanent magnet motor, so it can be an induction motor, right? So we can model different kinds of motors as well. So now let us look at uh, the different modeling aspects when it comes to the power electronics, right? So this is basically the inverters and different PCBs that you need to model. Right. So within COMSOL, the kind of simulation that you can do is you can take the multiphysics approach. Right? So if you look at this particular PCB model itself, you can start off with the basic electromagnetic analysis. And so within COMSOL, we also have what we refer to as the electric circuits feature interface as well. Right? So you can also create the electric circuits within COMSOL and also import any circuits from the external sources such as the spice netlist as well, right? So you can import those kinds of circuits and couple those circuits with your finite element model, the electromagnetic model, right? And you can couple the electromagnetic model with the solid mechanics, right? So where you're basically the electromagnetic interface is going to supply the magnetostriction and the Lorentz forces to the solid mechanics, and that in turn computes the deformations, right, because of those loads. So once again, the solid mechanics can pass on the information of different deformations and deformation rates to the acoustic interface, which in turn computes the acoustic structure interaction or the noises, or what we refer to as the pressure, the sound pressure levels in the surrounding air medium. Right? So similarly, the electromagnetic interface can compute and transfer the electromagnetic heating and core losses to the heat transfer interfaces, which in turn computes the temperature dependent materials and also the resultant temperature rise in your geometry. So similarly, you can model the different different thermal management methodologies as well. So it can be active cooling or passive cooling methodologies, right? So you can combine those with the various CFD physics interfaces that we have and perform any kind of, for example, conjugate heat transfer analysis, or it can be in order to model any active cooling where you model the different flow channels in the motor housing, right? So we can also very accurately consider the turbulence effect and so on, right? So, and of course, we have the general purpose optimization as well, where the objective function can come from any of these underlying physics interfaces, right? So, in essence, so you can do, you can consider all the real real world effects that are going on within your simulation model. So based on this, so study from Bosch, right? So this is multiphysics simulation, right? So this is for an inverter. So that is capacitors, and these are very critical components within the inverters, right? And they are basically, so they have very strict performance parameters when it comes to space and the temperature rise that it can afford as well, right? So here the engineers and researchers that were working on this basically coupled the electromagnetics effects with the heat transfer effects, and they were able to optimize this particular DC link capacitor to work in the optimum performance band. Yeah, here you can also see the measurement values compared with the COMSOL simulation results as well, right? Yeah, so this is another case study from them when it comes to the power electronics aspects. Yeah, so now we'll briefly look into the different battery modeling aspects as well, so within COMSOL. So when it comes to battery modeling, so in COMSOL you can start off with very basic, electrode level modeling as well, so where you consider the where you can consider the geometry from tomography assessments, right? So these can be very heterogeneous models, and you can start off with such very basic analysis, and then you can gradually homogenize it. So you can homogenize the properties at a cell level and ultimately to the battery pack level as well, right? So when you're going for very heterogeneous model route, so the results that you get out of it are going to be very accurate, but they are very expensive to compute if you look at it computationally, right? But as you go with more simplified approaches where you consider single particle models or lumped models, so this is going to give you results very accurately, but it is going to have a limited range of validity, right? So what is typically done is at the very electrode or cell level, it is going to be heterogeneous, and as you go to pack level, you're going to homogenize it for especially when you're doing any thermal management kind of simulations, right? And if we have to talk about scales, the different scales of battery modeling aspects within COMSOL. So as I was saying, you can start off with heterogeneous model, for example in this case the lithium ion electrode. So then you can homogenize it and do your simulations at the cell scale, right? So once again, you can consider different configurations when it comes to the cell, right? It can be cylindrical cell or a pouch cell and so on. And of course, you can consider your pack level as well, right? So where you perform either thermal management analysis, thermal management, or also thermal runaway analysis and so on. Right? So this is the kind of range and scale that COMSOL offers. So when it comes to the battery design aspects. Yeah, so now we have covered the entire gamut of modeling the different components when it comes to the electric vehicle drive. Right. So we also have what we refer to as the proof of concept model. So if you go to COMSOL.com and if you simply search for sync electric motor drive, right, so you'll be able to access this particular very high fidelity model. So this is a configuration that is very typical for mass market electric vehicle. So 8 rotors and rotor poles and 48 stator slots with skewed configuration, right? So V-shaped segmented magnet configuration, and so 325 hours, 460 Newton meters, 500 amperes of phase current. Yeah, so this is the typical configuration, and so this we have developed as a proof of concept and assess and basically to see if it is very relevant to the kind of simulations that you are doing within your team. Right? So we also have a motor tutorial series as well that takes you through step by step on how you can set up a very simple 2D model of a motor, and you can extend it to any kind of 3D simulations as well. Yeah, so for those of you interested, I urge you to obtain trial licenses if you are trying to do any such similar simulations. Right? And yeah. Okay, I think with this we have come to the end of the webinar. So So based upon the kind of content that you saw in this particular webinar and based upon your interest, so I would like to request you to answer this particular poll question. Right. So after this session, if you would like to connect with COMSOL team to discuss of any of your currently ongoing projects, or if you're facing any challenges when it comes to different simulation aspects, right, of your electric drivetrain. So if you want to evaluate COMSOL for any of your projects, right, so I request all the attendees to answer this poll question. Yeah, so as a concluding remark, I would like to say that electrification of automotive drivetrains has already started, and it has it has gained a particular momentum, right, and it is not going to stop anytime soon, mainly because of its reduced impact on the environment when we compare it to conventional drivetrains, right? So not just the electric vehicles, but also when we refer to different energy storage domains as well, right? So that is where we are seeing more adoption of battery storage, and also more modern technologies as well, such as the fuel cells and electrolyzers and so on. So in all of these, COMSOL has strong capabilities to model these at a very fundamental level, and also at a very stack level, or what we refer to as pack level as well, right? And not just a very basic underlying physics, which is the electromagnetics or the electrochemistry part, right? So you can also extend your such simulations by considering the different heat transfer aspects of it, so different cooling mechanisms that can be designed using COMSOL, or also the different structural mechanics aspects of it as well, right? Yeah, so yeah, I would like to conclude my remarks with these. So, and I urge and encourage all the attendees to explore more on COMSOL by either going for a trial license, or you can refer to more material on the electric drivetrain by logging on to comsol.com as well. Yeah, so if there are any questions, so we can take up the questions now. Yeah.
Thank you very much, Mr. Sharath, for the insightful and engaging presentation. I'm sure our audience found plenty of valuable takeaways. So now we will be screening the questions that have been posted by our audience in the Q&A box. We have received some great questions, so let's dive right in.
Okay, so we are particularly interested in the design and optimization of a synchronous reluctance motor and its drive controller. What are your unique offerings apart from multiphysics and efficiency mapping? Uh, yeah, so one thing is the different configurations that can be considered for modeling your electric motors, and apart from that, you can perform any for example, if you're since you're interested more in the controller modeling as well, so you can do co-simulation by connecting any simulation software such as the MATLAB as well. So MATLAB and Simulink that can be connected to COMSOL, and you can perform any sort of co-simulation, right? So the controller aspect or the drive aspect of it can be done in MATLAB or Simulink, and the finite element modeling aspect can be done in COMSOL, right? And so apart from that, if you're looking to optimize on each and every aspect of the underlying physics, right? So we also offer multiple and strong functionalities within the optimization, right? So we have very robust optimization solvers that are present, and yeah, so we have a large customer base as well that have appreciated such features and functionalities when it comes to optimization as well, right? How well can it simulate flux weakening, and does it also support advanced control strategies such as DTC, FOC for transient simulations? Yes. So this is basically based on the temperature dependency, and also the flux weakening because of large power demand as well. Yeah, so that can be definitely modeled within COMSOL. Yeah, and control strategies, like I said, so you can do it by by live linking COMSOL with any MATLAB or Simulink instances as well. Yes, that can be done. Can we calculate critical speed of electric motor? Yeah. So if you're talking about the critical speed for the uh, when it comes to the entire assembly of rotor and the electric shaft, so yes, that can definitely be done, right? We have different study types when it comes to the frequency domain aspect of it, right? So we can also calculate, like I was mentioning in one of the earlier slides as well, where we have plotted the Campbell diagrams, right? Typically, yes, it can definitely be done. You can obtain the different resonant modes and so on. Yeah, and we have a dedicated module for that, so which is the rotor dynamics module. So that is where you can do the shaft whirling analysis, basically the different to obtain the resonant frequencies, the excitation modes, and so on. Yeah. Okay, does it provide a custom cooling ventilation options, and is it possible to simulate manufacturing defects too, like misaligned laminations, winding placement, and so on? Yeah, so coming to the custom cooling part, yeah, so basically combining with the heat transfer physics interfaces, you can carry out. So you can either explicitly model the different aspects of your cooling system, or you can, we have what we refer to as the heat flux boundary conditions. So where you can implicitly, if you have the heat transfer coefficient data for your particular cooling uh, methodology that you have come with, so you can implicitly model the cooling mechanism to see how the temperature distribution is going to be. Right. Yeah, you can also model different manufacturing defects as well. Because of misaligned laminations, there is going to be different patterns of magnetic flux that is going to be formed. So yeah, all of this can be verified. Can I use pulse discharge data for lithium-ion cell characterization in COMSOL? Yes, you can do that, sir. There are various functionalities. So you can define different kinds of functions within COMSOL where you give this data, right? So the discharge data can be done, and you can perform. Yeah, you can perform such simulations.
So that was it with the questions. That was the last question that we have received. I would like to thank our audience for your thoughtful questions, and a big thanks once again to Mr. Sharath for the detailed responses. As we close this session, I'd like to extend our appreciation to everyone for joining us today, and special thanks to COMSOL for their unwavering support in organizing this webinar. We look forward to seeing you all again soon in another exciting session. The floor is now open for networking. Thank you all.
Yeah, thanks, Ala. So thanks everyone for your time for this webinar.
Thank you, sir.